Hello everyone, my name is Zhu Bingwu and I'm a PhD candidate from the Chinese University of Hong Kong. I'm very excited to have a chance to introduce my work in the MLCAD workshop, and I'm also grateful for my collaborators' help and advice. Okay, let me start the presentation. The title is Efficient Design Checking Script Generation via Key Information Extraction. First, let me give a brief introduction about the background and motivation of my work. As we know, design rule checking is an important step in EDA flow. It checks whether the layout conforms to a set of design rules. Here is a typical DRC process, which includes two steps. The first step is rule generation. Manufacturers first specify the essential design rules based on their manufacturing capability, and then convert them into executable DRC scripts manually. Then these scripts are provided to the designer and will be input into a design rule checker such as key layout to verify the correctness of the layout design. Currently, DRC faces several challenges, which makes the whole process time-consuming and error-prone. For example, with the rapid development of semiconductor technology, the number of rules is very large. Secondly, some design rules can be very complicated. For example, a single rule can be very long and difficult to understand, which may easily lead to misunderstanding during the script generation step. Thirdly, as shown in this figure, different checkers require different script languages, which means all scripts must be re-implemented when transferring to other checkers. In the last few years, advanced deep learning techniques have spawned some methods for DRC acceleration. For example, a work published at DAC 2018 designed such a flow where a neural network is trained to predict rule violations using features extracted from place analysis. However, these studies are not adopted by industrial designs. The main reason is that they still rely on manual rule generation to prepare the DRC scripts for design rule checkers. Considering such a situation, a problem naturally comes into my mind. Is it possible to accelerate the DRC script generation step in the traditional generation flow? In order to achieve this, we design such a script generation flow, which aims at reducing the manual efforts in the traditional flow. In our proposed flow, we utilize a deep learning-based key information extractor to automatically identify the essential arguments of the scripts for the DRC checkers, and the following translator will organize the extracted arguments into the final scripts. However, deep learning-based model cannot ensure 100% accuracy. The final manual correction is to guarantee the complete correctness of the scripts. Of course, the manual correction workload is determined by the accuracy of the extracted key information. Therefore, optimizing the performance of the key information extractor is critical to the efficiency of our flow, which is also the focus of our work. Okay, then let me introduce the methodology of our work. So the first question is how to extract key information from natural language design rules. Well, it can be converted to such a problem that a specific word should be classified into a particular category. The category is closely related to its semantic role in rules, and all categories we define will be explained in the next page. Now you can see the problem can be considered as a word classification problem. After finishing the word classification task, the categories and the related words can be paired, which is exactly the key information extracted from design rules. Okay, let me explain my defined categories for all words. I try to conclude all necessary key information. For example, the first category is object, which is used to mark the target layer of checking rules. The second one is relation object, which is used to mark additional layers that have relationships with the target layer. Some rules describe relationships that exist between two layers. One semantic rule I set is the restriction. For example, once there are some rules like this, which specify some geometry restrictions that the layer should follow. After defining all necessary semantic rules for all words in rules, the next part of our work is the raw data generation. So why we need to generate more raw data? Well, the open source design rules for academic research are relatively rare. Our training data set, FreePDK-15, only includes around 130 rules to help the model avoid overfitting as well as generalize better on those unseen raw data. We are supposed to expand the data set before training. However, raw generation for our task is heavily restricted. On the one hand, since the model receives the design rule sentences, we are supposed to guarantee that all the generated rules are both syntactically and semantically correct. On the other hand, as our task is a classification task, semantic rule labels need to be assigned to each word, which is extremely expensive. Considering these drawbacks, we need to design customized generation methods for our task. And here are three methods that I propose to expand our raw data. The first one is word order adjustment. We can change the word order of row without changing its meaning. Although for the human, the reorder sentence can be regarded as the same as the original one. However, from the model perspective, the input row is in sequence format. If the word order is changed, the input at each index will be totally different. What's more, adjusting the order will not affect the semantic row labels of words, and therefore no extra annotations need to be done. The second one is paraphrasing. In contrast to word order adjustment, paraphrasing can produce a new rule that does not change the meaning but has different expressions. Although paraphrasing will modify some words which requires extra annotations, there are still many words not replaced, whose labels also stay unchanged. Therefore, the annotation workload can be reduced remarkably. The last one is most important one. The generated design rules from the previous two methods are still confined to the meaning of original ones, which makes it challenging to generate enough training data. To take a further step, we propose third method, template filling. After applying the previous two raw data generation methods, we can obtain a series of design rules with diverse sentence structures. From these generated rules, multiple templates with different structures can be acquired. For example, here is the most common template, where the bold parts are specified semantic rows. With such a template, any suitable words associated with these prescribed rows can be filled. By filling in the designed templates via different combinations, a large amount of design rules can be collected for training, and we do not need to annotate the data manually. Then let's step into the generation flow. The first component of our flow is the key information extractor. The objective of this extractor is to identify the essential arguments from design rules to generate the final scripts. Here is the whole framework, which is not complex. Given the input rule, we first need some pre-processing operations and then feed it into the BERT module. BERT module is the backbone, and it is used for feature extraction. The next part is the word classification head, and it is used to classify each word into the predefined categories. Before I illustrate the details of the extractor, I would like to introduce some preliminary, which is about transformer and multi-head attention. multi-attention. Transformer is a very famous deep learning model which has made much progress in language processing tasks recently. So why is it so effective? Here is a key component of the transformer, the transformer encoder. The transformer encoder consists of multiple layers, of which the most important one is the multi-head self-attention. It allows the model to attend to information at different positions globally. In transformer encoder, the input sequence will be packed as a matrix, and the multi-head self-attention layer first projects the input matrix onto three subspaces as shown in the right part, and we call the three project matrix as query, key, and value. Then the output of multi-head self-attention layer can be formulated as follows, where HI is the output of single scale dot product attention. As for the scale dot product attention mechanism, it can be formulated into such an equation. The attention head then computes the similarity between projected query and key via the scale dot product, and a softmax function is applied to obtain the weights on projected value. Therefore, the relationship between each element within the sequence will be constructed, and thus the model has strong abilities to capture the global context information, which is critical for language tasks. Then let's see the model details. The first part is the pre-processing and backbone module. Pre-processing is used to split the rule into a list of words for the letter word classification task. Besides, since different rules vary in sentence length, we extend the word list length to a constant value. As for the backbone, it's used to obtain a good feature representation from the input rule. We know that determining the semantic role of each word is closely related to its sentence, and one word may have different semantic roles in different rules. For example, a particular layer might belong to an object category in one rule, but belong to relation object in another rule. Therefore, the backbone should have strong abilities to capture the context information, and we adopt a language model constructed from transformer called BERT. The structure of BERT is very clear. It is based on several transformer encoder blocks. Therefore, it incorporates the superiority of the global attention ability from the transformer encoder. In addition, another significant advantage of BERT is that it has been fully pre-trained by various language tasks on large data sets, so it has strong language representation ability. It's convenient to adopt BERT as our backbone and then fine-tune it for our task. And then the word classification head is composed of a two-layer MLP and a condition random field module. A two-layer MLP first outputs the score of each word belonging to each semantic role. Although this result can be used to conduct the classification task, it is not enough. This is because MLP does not consider the label relationship within the rule. To be specific, relation object is impossible to directly follow the object because there will exist a conjunction between them. Therefore, the model performance can be improved by evaluating the rationality of the entire prediction sequence. To achieve this, we build a probability model, condition random field on top of the word classifier, whose parameters are a label transition matrix, which describes the probability of transiting from label I to label J. Relying on the CRF, the probability of sequence is computed as follows. As you can see, it combines both the probabilities predicted by MLP and CRF, which is better for prediction accuracy. Okay, that's all about the key information in Stratter. Then let's step into the second stage of our flow, the script translator. The script translator in the second stage of our flow is used to translate the extracted key information into the DRC scripts. As we know, DRC script is composed of function calling statements. When given the key information, the functions to be called mainly depend on the checking properties. We can pair the properties and the function together. In addition to automatically pass the key information to the functions, we also need to connect the parameters of different functions with our semantic rows. As we clearly defined the fine-grained semantic rows before, the relationships can be easily established. For example, parameters that receive the layout layer name correspond to object or relation object, and the parameters that receive the checking value correspond to lower bound or upper bound or exact value. Okay, that's all about our flow. Finally, let me show the experimental results. The data set used for training our model contains about 3,000 design rules. Most of them are generated via our proposed data generation methods. To evaluate the performance of another design kit, ASAP7 acts as the test set, which includes design rules on the 7nm node. Because of the advanced technology node, rules in ASAP7 are more complex compared with our rules on the 15nm node for training. And therefore, the evaluation performance on ASAP7 will convincingly reflect the generalization ability of our framework. So, since our work is first one to investigate the key information extraction from design rules, no other sort of work can be referred for comparison. Therefore, we implement two baseline models, bidirectional RNN and bidirectional LSTM, which are also widely used for NLP tasks. The experimental results show that the accuracy of our model is satisfactory, which also means that little manual work is required in our proposed flow. In addition to the static accuracy, our flow also shows superior efficiency. According to the experimental results, our model averagely takes only 5 milliseconds to process a single rule. As for the translator, since it is simply responsible for deciding which function to call and passing the extracted key information to the function, the translation process is also high efficient. According to our measurement, the script translator spends only around 0.46 milliseconds processing one item of key information. In conclusion, by combining the extractor and the translator, our framework can generate a single script in 5.46 milliseconds on average, indicating that our proposed DRC script generation flow is extremely efficient. Okay, that's all for my presentation. Thanks for your listening.